Alright, so this is the Honors Chemistry Section 4.1 lesson video. And so in Chapter 4, we are going to start talking about the structure of the atom. So we're going to talk about kind of the history of how the parts were discovered, what does an atom actually look like, how do we know how many protons, neutrons, electrons, and things like that. So all matter is composed of atoms. So anything that's considered solid, liquid, gas, plasma, they are all composed of atoms. And an atom is the smallest particle of an element that retains its identity in a chemical reaction. So in chemical and physical processes, an atom can never change identity. Now it can change identity in nuclear reactions, but that's a different category by itself. So Democritus believed that atoms were indivisible and indestructible. Dalton also was very interested in the atom, and so he came up with Dalton's atomic theory, and so it had 4 points. His first point is that all elements are composed of tiny indivisible particles called atoms. So like carbon is only made of carbon atoms, hydrogen is only made of hydrogen atoms. Atoms of the same element are identical, the atoms of any one element differ from those of any other element. Now, atoms of different elements do differ from each other, but atoms of the same element are not necessarily identical, because we'll talk about something called isotopes later where they have differing numbers of neutrons. So this part about them being identical was not entirely correct. His third point was atoms of different elements can physically mix together or can chemically combine in simple whole number ratios to form compounds. Okay, so y'all, don't let something like simple whole number ratios throw you off. What that means is like water is H2O. So there's 2 hydrogens and 1 oxygen. So it's a 2-to-1 ratio. So water is always going to be H2O. It's not like it's going to be H4O3 sometimes. So the ratio is going to stay the same. And then his last point was chemical reactions occur when atoms are separated, joined, or rearranged. Atoms of one element, however, are never changed into atoms of another element as a result of a chemical or physical process. Okay, so remember, in chemical and physical processes, an element cannot change identity. So oxygen can bond with something else, and so it may look different in a reaction, but it's still an oxygen atom. We can't turn the oxygen atom into nitrogen or something like that. So the radii of most atoms falls within the range of 5 times 10 to the negative 11 meters to 2 times 10 to the negative 10 meters. Now we learned those SI prefixes and you had your SI prefix chart, but a lot of times you'll actually see the radius or diameter of an atom given in angstroms. Okay, so that's a different unit that's not on our SI prefixes sheet. And so that's just a convenient length for the radius or diameter of an atom. So 1 angstrom, and it's an A with like a little kind of degree sign above it, equals 10 to the negative 10 meters. So if you remember back to our SI prefixes sheet, we didn't have a 10 to the negative 10. We had a 10 to the negative 9 and a 10 to the negative 12. So angstroms is just kind of in the middle of that. If you could line up 100 million copper atoms side by side, they would produce a line only about a centimeter long. Now y'all, if you don't know what a centimeter is, it's about the width of your pinky. So 100 million copper atoms can fit across the width of my pinky. Despite their small size, they are observable with instruments such as electron microscopes, scanning, tunneling microscopes, but a lot of times still you get some sort of computer readout. It's not like a normal looking microscope where you just look in one end and see the other, but of course they're getting closer and closer to having better microscopes like that where we can actually just look at the atom itself. So let's look at our first sample exercise. All right, let me get my answer out so that way you're not stuck having to watch me use a calculator a whole bunch. So it says the diameter of a US penny is 19 millimeters. The diameter of a silver atom, by comparison, is only 2.88 angstrom. So remember, that's angstrom. How many silver atoms could be arranged side by side in a straight line across the diameter of 1 penny? Okay, well, we know the diameter of the penny is 19 millimeters, but the problem is they gave me the diameter of silver in angstrom. So if I want to compare the silver to the penny, I need to get the units the same. So I need to change angstroms to millimeters first. All right, so that's what I'm going to do first. So I'm going to do 2.8 angstrom. Alright, and then if you remember from the other slide, I told you that 1 angstrom is 10 to the negative 10 meters. Okay, so I follow my golden rule. Angstroms is on top, so I want 1 angstrom on bottom, and that equals 10 to the negative 10 meters. So angstroms cancel. Now I made it to meters, but I still need to get to millimeters because I'm trying to compare it to what they gave me for the penny. So I gotta keep going. Alright, so if you use your SI prefixes chart, you'll see that milli is 10 to the negative 3. And so I follow my golden rule, so I'm going to put meters on bottom. I'm trying to get to millimeters. So remember, it's 1 prefix unit equals 10 to the x base unit. I know some of y'all thought since we were done with chapter 3, all that must be gone. Converting never goes away, y'all, so I hope you get used to doing it. Alright, so 1 prefix unit, or 1 millimeter, equals 10 to the negative 3 meters. So then meters cancel, I'm left with millimeters, and so that's how I know I can stop. Just as a friendly reminder from Unit 1, any numbers on top you multiply, any numbers on bottom you divide by. So once I put that in the calculator, I ended up getting 2.88 times 10 to the negative 7 millimeters, and that equals 1 silver atom. Okay, because they told me that that is the diameter of 1 silver atom. So it says how many silver atoms can be arranged side by side in a straight line across the diameter of a penny. Well, y'all, once I know that this equals this, like the millimeters equals the atom, that is a conversion factor that I can use. So I know the penny is 19 millimeters. I'm trying to figure out how many atoms can go across it, so I follow my golden rule. Millimeters goes on bottom. How many? The amount I just calculated. 2.88 times 10 to the negative 7, and that equals 1 atom of silver. So my millimeters cancel. Since one number's on top and one's on bottom, I'm going to do 19 divided by this number. And when I plug that into the calculator, I get this right here, 6.6 times 10 to the 7 silver atoms. Okay, so a lot of times when you're doing a math problem, you gotta make sure your units are lining up and are the same. Alright, so that's all we have to do. And so we used our new conversion factor for angstroms. 1 angstrom is 10 to the negative 10 meters. Alright, so let's look at a couple more examples. And like I said, y'all, converting never goes away, so you're just going to have to get used to it. I don't know what to tell you. Alright, so you can try A, or you can watch me do A, and then you can try B, but just make sure at some point you try one. Alright, so it says the diameter of a carbon atom is 1.54 angstroms. Express this diameter in picometers. Alright, so y'all, I'm going from one unit to another unit with a prefix, so it's going to take me 2 steps. Alright, because I'm going to go from angstroms to the base unit, which the base unit for angstroms is meters, and then I'm going to go from meters to picometers. So it's kind of like 2 prefixes, although angstrom doesn't really have a prefix. Alright, so I start with what I know, and that's 1.54 angstrom. And then remember, our golden rule says whatever's on top has to go on bottom. So angstrom's going to go on bottom. So 1 angstrom is 10 to the negative 10 meters. So see, I got to meters, but it asked me for picometers. So I got to go one more step. Picometers is when we hadn't really used that often on your prefix sheet. So pico is 10 to the negative 12 if you look at your SI prefixes sheet. And so remember, we're going to follow our golden rule. Meters is going to go on bottom, and I'm trying to get to picometers. Alright, so remember, 1 prefix unit, 1 picometer, because that has the prefix, is 10 to the negative 12 base unit, which is meters. So meters cancel, I'm left with picometers, which is what we want, so I stop and solve. I'm going to multiply my 2 top numbers, there's a decimal here by the way, and I'm going to divide by that 10 to the negative 12. And so when I do that, I end up getting 154 picometers. Just like that. Alright, so like I said, make sure you pause it and try this one at least. You can use this answer for the diameter of a carbon atom for part B. So I'm going to assume you've paused it and tried it, and let's look at it together. So it says how many carbon atoms could be aligned side by side in a straight line across the width of a pencil line that is 0.2 millimeters wide. So this is similar to the sample one that I just showed you. So we know the diameter of a carbon atom in picometers, but we're trying to figure out how many millimeters, like we're trying to figure out how many would fit across a line that they've given us in millimeters. So I need to change picometers to millimeters. Since it's a prefix to another prefix, it's going to take me 2 steps. So I start with my 154 picometers. Alright, golden rule says picometers has to go on bottom. I'm trying to get to my base unit of meters. So 1 prefix unit, or 1 picometer, equals 10 to the x base unit. Pico is 10 to the negative 12 meters. So picometers cancel. I've made it to meters, but remember I'm trying to get to millimeters. So I got to have another step. So I follow my golden rule. Meters has to go on bottom. I'm trying to get to millimeters. And so then 1 prefix unit, or 1 millimeter, equals, if you look at milli, it's 10 to the negative 3 meters. My meters cancel. I'm at millimeters, so I'm ready to solve. Alright, so I'm going to multiply my top 2 numbers and divide by 10 to the negative 3. And when I do that, I ended up getting 1.54 times 10 to the negative 7 millimeters. And that equals 1 atom of carbon. Okay, so here's the conversion factor that I'm going to use next, 1 atom of carbon. Now y'all keep in mind, on this problem, you could have started with 1.5 angstroms and gone to millimeters. That's fine too. It'll work out the same way. It doesn't matter which one you start with. Alright, so last thing we got to figure out is how many carbon atoms will fit across this pencil line. So we know the pencil line is 0.2 millimeters in width. So I follow my golden rule. I'm going to put millimeters on bottom. How many? This many right here. 1.54 times 10 to the negative 7. And that equals 1 atom of carbon this time. So my millimeters cancel. I made it to atoms. And I'm going to take my 0.2 and divide it by this number on bottom. And so when I did that, I got 1.3 times 10 to the 6 atoms. All right. Just like that. So hopefully you got that one right. So like I said, y'all, as much as you might want converting to go away, it never does. So you might as well just get used to it, unfortunately. All right, the more you practice it, the faster you get, and then the more enjoyable it is. Like a lot of you don't like it because it takes you so long, but if you'll get good at it, then it's really fast and it's not that big of a deal. Practice, practice. That's all it takes. So in your own words, state the main ideas of Dalton's atomic theory. Okay, so y'all, we had Dalton's atomic theory on one of the previous slides. But it says in our own words, so let's try to shorten these some. So I'm just going to say them and you can write down whatever you want when you kind of rephrase these. So we can just say all elements are made of atoms for part 1. All elements are made of atoms. For this one, atoms of one element are identical, because that implies that atoms of different elements are different. We could say here, atoms can physically or chemically combine. Atoms can physically or chemically combine. And in this one, we can say atoms can never change to a different element. Atoms can never change into a different element. Or like I said, if you want to rephrase those in whatever form you want to, you're more than welcome to write that down. Alright, so according to Dalton's atomic theory, is it possible to convert atoms of one element into atoms of another? Well, hopefully you just heard the last point of that. The answer is no. Okay, not through any physical or chemical process. Now, however, remember, nuclear is its own separate category. Alright, so number 3, it says a sample of copper with a mass of 63.5 grams contains 6.02 times 10 to the 23 atoms. Calculate the mass of a single copper atom. See, y'all, whenever they tell you something equals something else, that is a conversion factor that you can use. So I can say that 602 times 10 to the 23 atoms equals this 63.5 grams. And so I can use that as a conversion factor. So it says calculate the mass of a single copper atom. So we have one atom. And so then I just follow my golden rule. atom is on top, so I'm going to put my atoms on bottom. How many? My 6.02 times 10 to the 23 atoms. That equals 63.5 grams. So my atoms cancel. I'm left with grams, which is what I want. So I'm just going to do 1 times 63.5 divided by 6.02 times 10 to the 23. And so for that, I got, I'm going to write it sideways here, y'all, because I'm running out of room. 1.05 times 10 to the negative 22 grams. Just like that. All right? So hopefully section 4.1 wasn't too overwhelming, just a little bit about the history of kind of the thought process of atoms. And then as we continue this chapter, we'll learn a little bit more about it.